So, yes, my name is Christian Koski, and I work as a research scientist in the Finnish Geospatial Research Institute in the National Land Survey. And first, I will just give you a short introduction to what we are doing and why in this hydrographic mapping part. You already touched on this, and then I'll speak a little bit about our experiences with producing training data for these purposes. So for this hydrographic mapping, the motivation is really that now with high resolution elevation models, it's easier to detect ditches and smaller natural streams, and to gain a better positional accuracy and completeness for these features in our topographic database. And these have really been quite challenging features to map in the past. And now also, as we are starting to map other features or derive them from elevation models, for example, these contour lines, they don't really match that well with this stream and ditch data, which is especially visualized on maps that can look a little bit weird. And also we are aware that recently researchers have achieved quite promising results from mapping ditches and streams using convolutional neural networks, so that acts as a motivation for us as well to start this kind of work. And here's an example of this positional accuracy. So we can see a small ditch here or a small stream, and then in the National Topographic Database, the feature looks quite bad, but this is an extreme example. They are not all like this. And then on the completeness, which is, I would say, a more problem, we can see 3 ditches here, but then one of them is actually missing from the topographic database. And these are the problems that we are trying to solve with this with these machine learning methods, at least trying testing at how well these kind of problems can be solved. So the goals here is to pilot methods for machine learning methods for automated mapping of hydrographic features, and we will really focus on small natural streams and ditches. So lakes and these larger rivers are quite accurately mapped already. And then we will also develop a prototype machine learning method for this purpose and assess the quality of how good of a quality we can get using machine learning to detect these features. And we'll use as an input data, we are hoping to use the National Land Survey's 2-meter resolution elevation model, because that is really just the highest resolution elevation model currently that covers the whole country. But then we also are interested in how good results we can get from elevation models that will be produced from these new 5 points per square meter point clouds. We started working with this a little bit later than the rest of the project. So we started in May, and we have so far been working on producing training data, and we have about 27 square kilometers of training data that has been digitized manually. And we are also expecting quite a lot of ditch data, accurately mapped ditch data from another project during the autumn. So we get a lot of data that we are hoping to use for this purpose. We'll have to assess the quality once we get that data. And then we are currently also exploring and experimenting and developing a convolutional neural network. And we have started some early experimentation, but I won't talk about that much today. And then we really need to develop this process for cleaning and vectorizing the results from the neural network. This you have touched already on, and then we'll assess the quality and we'll try to iteratively improve the method, and then we'll report on the final results. So now I'll talk about the training data and some challenges and how we have sort of tackled this training data, producing training data for our purposes. The first step is really to digitize these ditches and streams, and we have done it manually. And we have used some background layers to sort of highlight these from the elevation models, and really the main background layer we have used is topographic position index, layer, which is basically the difference of the elevation of a point and the mean elevation of its neighborhood. And that I'll show you an example in the next slide. And then we have used, as a secondary method, we have used hill shading, and then we have had an order photos and current hydrographic features from the National Topographic Database, but really those haven't been that much help because, as many know, Finland is mostly covered in forests, and you can't really see these features under the canopy. So here we see the elevation model and then the hill shade, which brings out these ditches quite well, but then the topographic position index really highlights them even further. And then we have quite a lot of challenges with this digitizing. There's some fuzziness in this stream, in these background layers, like we don't see the streams and ditches that well. This is a natural stream, and they are especially difficult to see from these. Well, they are not always clear if you go to in the terrain either, so they can be quite difficult to see some. Okay, so then we have like what we actually should map. What is there some minimum size of ditches and streams we would like to have? For example, here you can see that there's clearly these man-made ditches from the topographic position index, but then in the terrain it's really a very, very small and shallow ditch. Then we have these weird formations which are actually ditches, but well, as far as I know, these are left behind from forestry, or they are used in forestry for some reason. I'm not an expert on that, but they exist, and so far we have not mapped this, but we don't know really how that affects the end results. There's this kind of small unmapped pools and ponds, which are sort of a challenge because if we don't map those, then the ditch, which or the water flow which will actually flow through it will in the data it will be cut where the ditch then doesn't continue. But so far we have just left these unmapped, and maybe we'll have to look at them later and map them as well, maybe. Have to see. And then when we have digitized this data, then the second step of this is to turn them to training data. And here we are using just buffering. So we have basically digitized the center line of ditches and streams, and it's unclear really how we are going to do with the ditch width, because it's not always the same, of course, but our plan is to now not worry about it in the beginning, but we might make some tries with data that we have the ditch width digitized. So see how that affects the results, and then once it's buffered, we do association, and then we could also do some filtering for it. For example, reclassifying ditch pixels to non-ditches if the TPI at that point is more than 0. So that would mean basically that the point is higher than its neighbor, the mean value of its neighborhood, which would most likely mean that it wouldn't be an actual ditch. And this could be also a way to tackle this issue with that if we buffer a ditch too much, it could help for that kind of issue. And then we have identified some other data-related challenges. So we don't currently know quite accurately how much data we actually need. And then we also need to assess the need for data from different types of terrain. So now we have only digitized from one type of area all our data, but Finland is quite a large country with different kinds of terrains like swamplands and urban areas and mountains. And then we also want to understand how resolution of input data affects the results. But actually these are all questions that can be better answered once we start testing a model, and once we have developed a model, and can start testing with it. And that is as I previously said, that's the sort of work that we are right now working on to develop this model. That's all from me. So thank you.